In this video, we're going to show that you can use the recursive formula for the number of derangements to prove an explicit formula for the number of derangements. And we're going to do that by going through a slightly nicer recursive formula. So first, I want to take this formula n-1 times dn minus 2 plus dn minus 1, and I want to show that it satisfies this other thing. I think now, last video would have been the best time, but this is about the second best time to realize that this is not a linear recurrence because I have an n showing up in addition to these other things. So all those formulas we have for solving linear recurrences aren't going to do the job. So that's why we need to do some kind of special tricks here. So let's start by looking at this different recurrence. We're going to use induction. So we're going to use induction on n. Both of these have the same base case. They both basically satisfy d of 1 equals 0 by default, because this one has a dn minus 1 term, so I need to know what d of 1 equals. And this one has a dn minus 2 term, so it actually has two default cases. So for this one, our base case is basically going to be to show that the default case, basically, we want to show that the d2 that we kind of had to assume back here also satisfies this equation without just straight up assuming it. So I want to show that d2 equals 1. And we're going to go ahead and do that by saying that d2 is going to equal 2 times dn minus, or d of 1, plus negative 1 squared. That's going to equal 2 times 0 plus 1, which equals 1. Yay, base case is done. Okay. For our induction step, I'm going to start by assuming, and this will look rather similar, or rather nice, we're going to assume that this is true for dn minus 1. So if I go ahead and replace everything with an n minus 1, I'll have n minus 1 dn minus 1 plus negative 1 to the n minus 1. We'll say for n minus 1 greater than or equal to 1. That's a lie. It has to be greater than or equal to our base case, so greater than or equal to 2. So we're going to assume this. Note that if I, first of all, negative 1 to the n minus 1 is going to equal negative 1 to the n. And if I add that, if I add negative 1 to the n to both sides, what I'll end up with is that dn minus 1 plus negative 1 to the n equals n minus 1 dn minus 1. And if you notice, that shows up in the formula I already have. So let's go ahead and use that formula. We know that dn equals, I'm going to go ahead and distribute this out just to make my life easier, n minus 1 times dn minus 2 plus, and for the record, before we get too far, there was a mistake there, which we will correct now, because I just defined dn minus 1 in terms of itself. Nope, that's wrong. These should have been oh no, that one was right. That one is supposed to be a dn minus 1, but this one is supposed to be a dn minus 2. Okay, let's fix that. So dn equals n minus 1 dn minus 2 plus n minus 1 dn minus 1. And let's substitute this part in for n minus 1 dn minus 2. So this will give me dn minus 1 plus negative 1 to the n. Plus, let's go ahead and distribute this over here. That's going to be n dn minus 1 minus dn minus 1. Hey, look, those dn minus 1s cancel. And we end up with, rearranging some things, n dn minus 1 plus -1 to the n. And that's it. So we went ahead and proved that if that first recurrence is true, then the second one is also true. So we now have two different recursive relationships defining the formula for derangements. And now that we have that, I can now prove this general formula for the derangements. So let's go ahead and do that. We're once again going to need to use induction, but this will be a rather quick induction. So does this work for D1? D1 does in fact equal, let's see, what's the sum from, this should probably, oh, that is supposed to be 0. I'm right there. That's going to be the sum from k equals 0 to 1 of -1 to the n times, sorry, that shouldn't be n, that should be a k. It'd be really boring if that was n. Same here, that should be a k. And then we're going to have n factorial, which in this case is 1 factorial, over 0, or k factorial. And if you break this up, this is going to be 1 times 1 factorial over 0 factorial plus -1 times 1 factorial over 1 factorial, which equals 1 minus 1, which equals 0. So that's good. Now, we're going to assume that d of n minus 1 equals, I'm going to take my formula, replace everything that's an n with an n minus 1. We'll have k equals 0 to n minus 1 of -1 to the k, n minus 1 factorial over k factorial. Then d of n, well, that's just going to equal n times d of n minus 1 plus -1 to the n. And I'm going to do some funny things here. First, this isn't terribly creative. I'm going to replace dn minus 1 with my sum that I have here. N minus 1 factorial over k factorial. And then I'm going to write this last term a little silly. I'm going to write this as -1 to the n, and just for fun, I'll write it as that over n factorial, or times n factorial over n factorial. Well, let's go ahead and simplify this a little bit. I can move that n inside, because it doesn't depend, well, I can just move it inside, period. And when I take n times n minus 1 factorial, that's just going to become n factorial. So this becomes k equals 0 to n minus 1 of -1 to the k, n factorial over k factorial, plus -1 to the n factorial over n factorial. And what we notice is that this is exactly the next term in this sum that we didn't include, so I might as well just go ahead and include it in there. So that's going to be -1 to the k of n factorial over k factorial, this time going from k equals 0 all the way up to n. And there we go. We proved that this explicit formula works by using a recursive formula for the number of derangements that we derived from another recursive formula for the number of derangements. So this formula works. Great. In the next video, I'm going to get you started with seeing how you could prove this using inclusion-exclusion. So that's where we'll go next.